Hey guys, welcome back to our last presentation before lunch. Up next is David Jorm from, where are you from, David? Spider Labs.
It's on the slides, yeah.
Yeah. So I have this problem reading, you know, it's this thing I have. David's going to present on penetration testing Android applications and embedded devices, so please welcome David.
Hey everybody, is the sound level okay? Yeah? Cool. All right, I'll start by giving you a bit of an introduction. The photo is just there for if I distribute the slides later and people want to gaze upon my magnificent visage. I've been in the computing industry in various ways for 18 years. I'm 35 now, so officially more than half of my life, which is a little bit depressing. I started out as a Linux sysadmin for a little ISP in Sydney. Found out they were actually paying me below minimum wage, but anyway, I was 17. And then I became a climatologist. I worked for the Bureau of Meteorology. I got a mathematics degree. My claim to fame is I built Australia's aviation MET system. So whenever you're flying around the country and the pilot comes on and says, all right, we're coming into land in sunny Brisbane and the temperature on the ground is 23 degrees, light, north-northwest breeze, I wrote the system that collates all the data and generates those messages and sends them to planes. And the whole thing is written in 100% PL SQL. It's a bit of a nightmare. After that, I moved to Red Hat and worked on their documentation, eventually became the manager of their product security team. And so obviously that involved a lot of products that are built on Linux and a lot of products that are built using Java. So a natural extension from that was moving into Android because it's built on top of those two technologies. I still do a lot of work in open source communities for the Linux Foundation and so on. But now I work for Spider Labs, the practice lead for Asia Pacific and the global lead for mobile testing. So what we're going to talk about today, here's the overview of everything. It's going to be fairly high level and it's going to have a few live demos. I'm not going to give you any elite RCE techniques. This is more about, I think a lot of people would say, okay, I'm going to pen test a network, I'm going to pen test an app. I have a vague idea of where to start and what I'm going to look at. If somebody handed you an Android application, would you know where to start? If somebody gave you a VoIP phone and put it on your desk that's built on top of Android, what would you do with it? Where would you begin? So the point is to give you those kind of tips more than anything else. So at a high level, that's the architecture, and I know with such a complex diagram, it's going to be difficult to pull everything apart. But basically, just look at the layers. And I'll start at the bottom. At the bottom, you have the Linux kernel, which is controlling all of the hardware, interfacing with all of the hardware. And then above that, you have a whole bunch of libraries. And again, this stuff is all just sort of standard Linux libraries, like you would have on any Linux system. Then the interesting part is the Android runtime. So the Dalvik virtual machine, it's been renamed now, but anyway, everyone still calls it Dalvik, is very similar to a Java virtual machine. And every single application runs on top of the Dalvik VM. We'll go into that in more detail later. But this is where you start to get the unique, what Android does that's not just Linux. You have the Dalvik VM, then on top of that you have an SDK, an application framework, where Android exposes things at a high level. So Android applications aren't just making Linux syscalls to do everything, they're calling these Android libraries that do things at a high level and that will do mobile specific things, like I want to read data from the accelerometer, or I want to read data from the location services, the GPS. And then at the top level you have the actual applications that run on the device, and that's what we're mostly going to be looking at. So take a look at that in more detail. The applications themselves are written in Java, and there's a few reasons why they chose that. Obviously, I can't ascribe particular motivations to Google, but I think a big and obvious one is the fact that so many people out there can code Java. I used to be an engineering manager for a Silicon Valley startup, and we had a piece of the software that was written in Python and a piece of the software that was written in Java. And fucked if I could get any Python developers. But the Java developers, just hundreds of resumes, all the time. So that's an obvious reason. So Java obviously is a platform agnostic language, which also helps with mobile devices because although most of them are ARM, there are multiple architectures that are used, and even ARM32 versus ARM64. So by writing something in a high-level platform agnostic language, you can compile once, run anywhere. So the Java compiler compiles it down to class files, which is Java bytecode. Now, Dalvik takes it a step further, and then the DEX compiler compiles Java bytecode into DEX bytecode, and then you package it up with all of the metadata around the code, which we'll get into later, and that becomes your APK file. That becomes your actual application. So why would you You've already got Java bytecode. Why would you go another step and create another level of bytecode? It doesn't really make a lot of sense to do that. So first thing about Dalvik, it doesn't use the Java Security Manager. So typically, if you want to sandbox a Java application, you use the Java Security Manager, which allows you to blacklist or whitelist permissions. Just say things like at a high level, okay, this application cannot read files from disk. This application cannot, open arbitrary sockets or whatever, right? You can set granular permissions on what an application can and can't do. And the JSM is a great idea, but a god-awful implementation. So its main use is, if you remember back when everybody used to have Java applets running in your browser, the way that they stopped those Java applets from just executing arbitrary code on your machine was by using the Java Security Manager. And there's been something like 100 bypasses for the JSM, which is largely why nobody uses Java applets anymore, because of the security implications. So I'm glad they didn't use the JSM. That would have been a bad decision. Instead, the sandboxing is performed by the Android libraries at the operating system level, and we'll get into sandboxing in a minute. The big reason for using Dalvik is that there's performance enhancements over the JRE because it does combine native code. So even though you write your Java code once and it can run anywhere, when you compile it, it will compile into different architecture packages, and those are all included in the one APK file. So that gives you a performance boost, and on mobile devices, particularly cheap mobile devices, that's actually really important. Okay. So this is the sort of key part of Android application security, is that it's a multi-tenanted environment. You've got one Android device and multiple applications. Obviously, you do not want one application to be able to read or write the resources, be it memory, files, etc., of another application. So you need a sandboxing environment to do that. So the way that it works is each application has its own process that it's running on, which is a Dalvik VM process. It's got a unique instance of the VM. It's got its own process ID, because it's its own process, and it's got its own user ID. So by default, you install an app, and it creates a user just for that app. And every app has their own user. And then beneath that, every app has its own data storage directory, which is owned by that user. So at the Linux kernel level, nobody else can read or write those files, just based on simple file permissions. So that's how sandboxing is achieved. Now, the other thing is there's a permissions model in addition to the sandboxing, and that's sort of a bit more like the Java Security Manager that I was talking about, where you say what the application can and cannot do. But it's in reverse. With the Java Security Manager, the platform hosting the app sets a policy and says, this is what you can and cannot do. With the permissions model, the Android app says, this is what I need to do in order to be able to execute. And it does this by defining in Android manifest.xml, which is one of those metadata packages I was talking about, what kind of permissions it needs. So there's some examples. Now, those are the two permissions you need to just do, in the case of my sample app, I want to make a call to a HTTP API. Those are the two permissions I need to be able to do that. And those two permissions fall under the normal category. So if you install my app, it won't prompt you for anything. It won't say this app needs to call an API. It will just install. If I want to do things that are more dangerous, like say, read your contacts, send and receive SMS messages, read your SMS messages, etc., this falls into the dangerous category. And that's when you install the app from the Play Store and it says, do you accept this app can do the following things? And either you accept or you can't install the app. And then finally, there's the signature category. And this is used largely by suites of software. So I don't know for a fact, but I'm 99% sure. Say you've got Gmail and Google Maps on your phone, and you sign into Gmail once, but then you go into Google Maps, and it knows who you are, and it remembers your history and everything. That will be because they have a permission to share data, and that's at the signature level. So because they were both signed by the same authority, the packages were both signed by the same cert, not same authority, then they're able to share that permission. So data storage generally is fairly safe. We've got that sandboxing model. We still do need to be very careful about what we store, because there are various scenarios in which people could extract that data. The obvious one is once they have physical custody of the device, they can do anything. They can get data from any of these. The other is if there is some kind of vulnerability in the sandboxing environment, then one application can read data from another application's directory. So generally, you don't want to store sensitive things even on that private storage. And I've seen this in apps. They store all kinds of ridiculous stuff, your plain text creds, your credit card number, because they think it's all sandboxed. But even more dangerous is external storage. And I think from reading the history, this came from the early days when you'd buy a device and would have like 32 megs of storage on it, and that was just enough for your operating system. And then you'd have to put an SD card in it, and that's where you put all your data. So that external storage referred to your SD card, and it has no permissions. It's like /TMP. It's just anyone can read or write whatever they want. And these days, it doesn't necessarily even have to be a separate physical SD card. Every Android device will have both internal and external storage. So a major issue that we see in Android apps is simply writing anything vaguely sensitive into external storage. And people do this, like, for example, you might get a messaging app, right, where you can send images to each other, and they'll put them in external storage because you think, oh, it's just an image. But obviously, if another app can then read those out, that's, it's potentially a very serious security issue. So in addition to file storage, Android kind of has, obviously you could do whatever you want because it's Linux, but it has sort of integrated native support for SQLite, which is just a very simple single-user SQL database where the whole database is just stored in 2 files. And I'll give you a quick demo now of interacting with that database. And this will give you an idea of some of the tools that are critical when pen testing Android applications. So the most important thing is Android Studio. Android Studio is just an integrated IDE, SDK, virtualization platform for Android development. And it has this thing called the AVD Manager, which is the Android Virtual Devices. So we'll go through it later, but you can just set up what is effectively a virtual machine of an Android device. And this is much, much easier for testing applications than a physical device. You can do all of this using a physical device, but it's much easier using a virtual device. So I've got this phone. I want to start to have a look on the file system. Where do I start? So there's a thing called the Android Debug Bridge, or ADB. And again, this can be done with a physical device. I've got a S8 here. If I plug this thing in via USB to my laptop, it will prompt me saying, do you wish to enable debug mode, I think it's called, on this, which means that if I said yes, then I could use ADB from my laptop to the physical device. And it's basically like an admin interface or a debug interface. When you run these virtual machines, it does that by default. So yeah, you get this platform tools directory, which has all these different tools to interact with your virtual machine. So if I do ADB shell, it just drops me into a root shell on the device, and now I can do whatever I want. So pen testing an app, that's basically the first step for me, is spin it up in a virtual machine, get a root shell, now I can poke around and have a look at whatever I want. So the app that I'm going to look at is this little Android CTF that I made, which if anybody is interested, just hit me up and I'll give you a link. So every application, if I go back a level, every application just has its namespace and it gets a directory for that namespace. Oh, oops. So you've got a standard layout in here, cache, code cache, databases, and files. If you go into the databases directory, that's where you'll get SQLite. I made this silly Dapto database because I lived in Dapto once, and that was a bad idea. So yeah, you can dump out the schema and so on. Query things. It's just a standard SQL database. But again, that's a very interesting place to start looking. If you're pen testing an app, what's it storing in the database? What's it storing on disk in the files directory, etc. Yeah. There we go. Okay. So that's looking at storage, permissions model, etc., everything that's on the device related to the application. That's sort of half of the attack surface. The other half is what it's doing over the network. Any application that's doing anything vaguely interesting, even a game, it's going to be communicating over the network. If you're playing, you know, I don't know, one of those stupid Candy Crush games or something, it's got to send your score off to a server and get the scores of your friends back and so on. So there's always some kind of API. If you've got a kind of peer-to-peer messaging app, there's going to be peer-to-peer comms. If you've got a voice app, there's going to be, you know, XMPP data or something. So this is a major attack surface, and there's nothing really special about it. It's the same as any application, be it a web app, be it a thick client app that's communicating over the network. Obviously, that's something that you want to test. So the main thing is to understand how to do that. If you have a thick client app or a web app, you spin up Wireshark, you spin up Burp, and boom, I'm intercepting all the traffic, I'm done. Here it's a little bit more of an involved process to be able to actually test and intercept all of that traffic. So I'll be looking at Burp here. Same thing applies for Wireshark, but obviously Burp is what most people would want to play with. So basically you just want a routing setup, just the same, you know, if you replace Android VM with web browser, this is the same as a standard Burp setup. So I'll show you how to do it, and it's surprisingly complex. This is something that I'm going to put a gist up on GitHub because there's no good documentation around it. The first time I did it, it literally took me a whole day, like a 10-hour day, to figure it out from Stack Overflow and all kinds of stuff. So we will start from scratch by creating a new VM. I use, again, this is one of my learned pieces of wisdom. Nexus 6 just always works. Everything works. So use that. API level 23 always works. And we'll call it AusCERT. So it's a pretty cool virtualization platform like that. Once you've downloaded the OS images and it comes with the base frameworks of all of the different device types, then you can just, as simply as that, create a new device, launch the device. In a second. Go back to that one and create. So that'll take a moment to come up. While that's happening, in the background here, I've just got a standard Burp set up. How do I? There we go. Clear history so we can see it from fresh. The only thing that we have to do is in the Options tab, set it to listen on all interfaces. By default, it's only listening on loopback, but here we're going to have a bridge interface that the VM is using to talk to the host, and that's the interface that we need to be listening on. So we just listen on all interfaces. Okay, so we've got this device. So the standard things you need to do to set up Burp in your web browser is you need to install the certificate, and then you need to set Burp as your proxy server, right? So we do the same thing here. Like I said, I'm going to put up a gist with all these steps, but just to give you the gist of it, sorry. Okay, that's great. Of course, that's never happened to me before and happens the day that I try and do a demo. Yeah, fantastic. There we go. Okay. It's just a bit slow. So we need to go down into the security tab. And the first thing you need to do is set a screen lock. It won't let you do some of these subsequent steps if you haven't set a screen lock. So we'll just make it all 8s. Confirm our PIN. Okay, we're done there. Now we need to install the certificate. So another thing that ADB can do for us is just push arbitrary files to the device. DR, so we'll push that to the SD card. We have to call it .cer for whatever reason there, the file's there. So it's a very convenient system for debugging and pen testing. So then we have to go down to the credentials, install from SD card. We don't, for whatever reason, select SD card, we select internal storage. That took me a while. Import our certificate. So there you go, the certificate's installed. So now all we have to do is set the proxy. So we can go into networks. By default, you can change it, but by default, it will give you this virtualized APN from T-Mobile. I don't know how much that cost T-Mobile for the product placement. But you can go in there and you can set, at the level of the APN, you can set a global proxy server. And this will proxy all HTTP and HTTPS traffic through the device. Actually, it will proxy nearly all traffic through, like XMPP and stuff will work as well. So it's always, your host bridge is always 10.0.2.2. So we set that as the proxy. Port is 8080. We have to save. Now we're done, right? That's it? Everything's done? No, not quite. This doesn't work unless you toggle airplane mode, which, yeah, that one took me a while as well. So now we can go into a browser. And if the demo gods are smiling upon us, if my Wi-Fi works, there you go. You'll see history coming up in burp. And you can verify that it's my mobile traffic because you can see it's from the Android browser. So yeah, that's pretty much how you start intercepting and debugging network traffic. And at that point, it's a standard application pen test that you can go on with. So embedded devices. This is where it starts to get interesting. So what we're talking about here is not Android itself, but everything that's built on top of Android. And one flavor of that is just a standard application that you can install. The other is people put Android into a physical device and then start building stuff on top of it. This is very, very common. The vast majority of things like VoIP phones, various IoT devices are built on Android. Because it's free, it's open source, you can write your code in Java, it's Linux, every reason under the sun to do it. And the problem here is the OEMs just screw it all up. Android itself is a great system, but then these OEMs come in and just hack on top of it and build all kinds of garbage. And actually, quite a lot of the jailbreaks, the rootkits that people have found have been, for example, in phones, in software that the OEM has pre-installed, not in Android itself. So I wanted to give you a case study here of a single IoT device, rather than give you a bunch of stats about how many IoT devices there are and whatever. Let's hack something. So I used to work for this Silicon Valley startup called Console. I think they're about to go broke. And one day I was sitting there in Santa Clara in this cavernous office with no people in it, and there on my desk appears out of nowhere this phone. The IT guy's come in overnight and he's installed these VoIP phones. And I'm looking at it and I notice it's got an IP address. I don't think you can see it. No, you can. You probably can't make it out. But that little white strip at the top of the left-hand bar, it's got your IP address. And so I thought, okay, let's have a look. What do we have? So yeah, it's an Android-based VoIP phone. The best thing is, we got root, of course, we'll get to that. But it integrates with a door opening system. So the idea is somebody buzzes you, their image comes up from the security camera on your phone, and then you hit a button and go, yes, unlock the door, let this person in. So yeah, potentially quite dangerous. So first thing you do, you nmap it, and it's got an SSH and a web interface. They both require authentication by default, so all right, this isn't too bad. What could go wrong? Well, of course, there's default credentials of admin and user123, and they're documented in the user guide. I don't know how many sysadmins would actually change them, but I guess some would. Very conveniently, it gives you a remote code execution API in the web interface. So as you can see there, you just run the exec command action and put in your command and off you go. So that was a very convenient helper from the developers. So straight away we have RCE, but we're depending on these default credentials still being in place. So yes, it's RCE, but does it really count? Does it cross a trust boundary? Is the question. And you would have to say, well, no, because theoretically, sysadmin's meant to change the defaults. So, what can we do? So the other way in that we found was to SSH in. Now, SSH gives, once you SSH into the device, you get this shell. Now, the way that we're able to cross a trust boundary here is that you can SSH in as the unprivileged user. as user123 rather than admin. And the idea is that every user should in fact have credentials because they can use it, for example, to lock their phone. And that's what they use those credentials to unlock it. So once you have these credentials, you can get into this SSH interface, which only allows you to do a certain number of things. It does allow you to format the user data partition, pardon me, but that just lets us wipe data. It doesn't actually give us RCE or anything. So the interesting one here was ping and traceroute. So how would you implement this? You've implemented this little SSH wrapper to ping and traceroute. And of course, they're just wrappers to the shell commands. So we can just do straight up command injection on this. The only problem that we found was that by default, we're only getting std not std out. So we just redirect that. And then all of a sudden, we have root. Because, of course, why would you make this run as an unprivileged user when you can make it run as root? Now, here's where it gets really interesting. As we were poking around, we noticed that by default, there's an authorized key in root's authorized keys. And dug up this guy, J.H. Zhao, and based on his GitHub, he works for the manufacturer. So the question is this an honest mistake, that while he's developing everything, he just puts his own key in there so he can easily SSH in? Or is this actually a manufacturer backdoor? So we went to the manufacturer and said, hey, we're giving you the benefit of the doubt here. What happened? Can we ship a patch? And they said, no, we vehemently deny that this is an issue. You must have both a key and credentials to log in via SSH. To which we said, no, you don't. Look, I put my own key in here and demonstrate it. And they said, no, this is slanderous. We're going to take legal action if you publish this information because it's not true, and send us like threats from a lawyer. And so then finally we made a video for them. We went through the whole thing step by step in a video and sent it to them, at which point they deleted all their comments from our public blog, never replied to any email again, and withdrew their legal threats. So they never actually patched it. So if you have any one of these phones, they still do have a root backdoor in it. Now, the interesting thing here is this has got nothing to do with Android, but it's the fact that it gives you this base on which you can it's just a Linux platform with an application environment built on top of it, and then you can do whatever you want. You can put an SSH key in root's authorized keys. You can create an SSH interface with command injection. There's nothing actually stopping you doing that. And that's what we see with a lot of embedded device manufacturers that just take Android for granted and then build crap on top of it. So I think there's a lot to be found in this field. I think people talk about IoT security at a very high level, but I think at a specific level, you're just going to see instance after instance of this kind of thing. So yeah, quick presentation. That's everything I had, but we have plenty of time for questions if anybody has any.
Instance after instance is a rather bleak story, given Mirai and the other things we've seen over the last 12 months. What can the industry do to help stop this happening going forward?
Yeah, that's a great question. And I think the issue here is everybody doing their own thing again and again. If you look at something like, and I'm not saying it's perfect, but if you look at something like Android, it's one system built by Google who has a huge amount of resources. They have a great security program. It's not perfect, but it's secure. It's a good system. And then people just build arbitrary crap on top of it. It's like, how often do you actually get, remote unauth RCE in the Linux kernel or something like that? It doesn't really happen. So I think the problem is people building things over and over again. And a lot of people started to say this when the app ecosystem came out, that we had this framework of web applications where we built everything up, and now you just, as the developer, you just have this thin layer at the top. But now with the app ecosystem, it's going back to, you can do whatever you want, you can build everything custom, and everybody can make the same mistakes again and again. It's the same with IoT devices. So I think the only viable solution is to have more packaged, to package this stuff at a higher level. Every device is going to want some kind of debug or admin interface. Can we get a standardized one, rather than everybody putting together another shitty web application, another shitty shell script that wraps SSH? I think that's the only viable solution that I can think of. Anybody else?
Bueller.
Bueller? No?
No.
Okay, well, thank you very much for your time, everybody, and I hope you got something out of this.